So this video was from a comment left on one of the last videos where this user requested a video on Friedel-Crafts using just ACL3, which I'm not quite exactly sure what they mean there, and a harder example other than just benzene. So we can definitely give them a little harder example. So let's see what we can do here today. So you guys know the deal is predict the product based off the reaction conditions. Right here, we have this 1,3-dimethylbenzene, and we have two steps. So we're going to react it with chlorobutane and trichloroaluminum. And the second step, we have acyl chloride with trichloroaluminum again. So what's the product going to be? So let's work through that. So step one here is this alkylation with chlorobutane and aluminum trichloride. So as you know, Friedel-Crafts, you need this Lewis base as our catalyst, and it's going to give us this carbocation here, where we have the positive charge here where the chlorine was. If you want to know the mechanism for Friedel-Crafts, I'll make a video on that later, but right here, we're just going to run through the reaction. So you might think that this adds onto the ring, but that's not actually what happens. If you remember anything about carbocations from some of the other videos, primary carbocations are not very stable. So what you're going to get is a carbocation rearrangement, and we're actually going to get something that looks like this. And where you have a secondary carbocation. And this is much more stable. And there's no tertiary or tertiary position for it to go to, so it's going to stay as that secondary carbocation. And then this is going to be electrophilically attacked by the ring. And you're going to say, well, where is it going to attack? So these methyl groups here, those are electron donating groups moderately, which means they're ortho and para directors. And if you want to learn more about directing groups with electrophilic aromatic substitution, I can make a video on that later as well. But these are both ortho para directors. And then remember, so relative to this methyl here, this is ortho, this is meta, and this is para. This means it prefers these positions here. So when you have multiple directing groups like this, I like to kind of do a little score sheet of what it is. So I'm going to use green for the positive direction or where it's favored. So starting with this first methyl up top, where it's favored at the ortho positions, and then it favors the para position. And then it dislikes this meta position. I'm not going to mark this one because there's already something there. And the second one, it likes its ortho positions where there's already something there, and then it likes para again. And it also hates this meta position, which they're the same. Luckily, in this 1-3 configuration, they really have complementary directing. And so you've noticed all three of these spots has a green dot. So you say, well, which one's it going to go to? Well, if you look at it, there's actually an internal plane of symmetry right here. So these are the same spot in terms of chemical equivalence. So even if they added equally at all three spots, you'd actually get twice as many of these than these. But there's another thing in effect here. So these CH3s are not just little dots like this. They have, like I said, 3 hydrogens out here, which makes this spot kind of sterically hindered. And it would be trying to grab this. If it's grabbing it from here, that's kind of sterically bulky and hindered. So realistically, it's probably going to grab it from here. So that's going to give us our product. Where's my pen? It's going to give us our product that looks like this. Sorry that my benzene's not perfect. We're going to have our methyls, and then we're going to have our butyl group there. And that's how that's going to add. And remember, it doesn't matter if it adds here or here because those are chemically equivalent. It's going to give you this right here. So just remember, the directing groups are important, but also the sterics are important as well. So in our second step, we have another Friedel-Crafts addition, and this time it's not an alkylation, it's an acylation with this acyl chloride or acetyl chloride, however you want to say it. So just like the last time, we have our Lewis base, which forms our intermediate, which in this case, wrong color, which in this case is what's called an acylium ion, I believe. Don't always know the names of some of these things, but I know what they look like. So This right here is super reactive. You have a carbon double bonded to an oxygen with a positive charge on it. That's really electron deficient. So it's looking for some electrons and it's looking for them now. So now we look for our ring, and this is where's it going to add? So the sec butyl group, similar to our methyls, is also moderately electron donating. So it's also an ortho para director. So let's do our little checklist again, and we're going to start with the sec butyl group. So its ortho positions are favored. There's already the methyl group in the first one, so we're not going to check that. And it likes this position. Then in its para position, there's already something there. Nothing else is going to add, so we'll leave it alone. And then it dislikes these meta positions here. Our methyl group at the top position likes its ortho position. There's already something in its other ortho position. And then it likes its para position. And it dislikes the meta position. And then same for the other methyl group. It likes its ortho positions. And it dislikes its meta position when there's already something in its para position. So as you look at this, you say, well, there's a couple of places this could add. And what do you do when you have competing directing groups? Well, you go usually based off priority, where say like an OH is a better directing group than a methyl, so the OH would take priority. But here we just have all alkyl groups, so realistically, they're probably roughly equal. And so if you just look at our little check marks, based off this, you assume they would add at this position or this position. So how do you determine it? Well, based off just these drawings here, there's realistically probably not a way to say definitively which one would add. We're probably going to get a mix of two products that looks like this down here, where one adds in between the two methyls and one adds on the other side of that methyl. I don't think it would really add here that much because that's be more deactivated than activated. Also, like that butyl is a little bulky, so I don't think so. My guess is both of these would form, but this is my guess would be the predominantly formed products. This would probably be your major product, and that is because the same reason why our sec butyl formed over here instead of over here is because sterics. This position right here is much less sterically hindered, so it's easier to come up and grab this acylium ion. But like I said, we can't predict for sure. So realistically, in real life, more than just one product wouldn't form. More than one product can form, and it happens a lot. Trust me, as a synthetic chemist, it's very frustrating. So in reality, to do this, you'd make this, you'd make both, and you'd have to find some way to separate them, probably through a column, which if you run a column, they're not fun. But this is a great example as to how directing groups can get a little tricky. And so hopefully this was a tougher example than just benzene. Okay, so we got to the end of our first requested video where we had Friedel-Crafts alkylations and acylations. We started with this 1,3-dimethyl benzene. We alkylated it with this group here, and then we acylated it with this group here, which gave us two products because of competing directing groups. So just remember when you're doing any sort of electrophilic aromatic substitution, especially Friedel-Crafts, always watch out for that carbocation rearrangement because a primary halide might add as a secondary group depending on sterics and carbocation stability. And then if you have multiple directing groups on there, consider the competing directing groups and their competing preferences. If you have multiple ones, consider which one takes priority, which one's a better electron donor or electron withdrawer. So I hope this was a good video for you guys and a better example than just benzene for the person that asked for this video. I hope this was a little tougher for you. So if you're struggling with organic chemistry or you just want to improve your knowledge base in organic chemistry or make sure you keep getting those A's, be sure to hit that follow button. And if you want to see more videos like this one that was requested, be sure to drop in the comments what you want to see. And then if you have any questions about organic chemistry that you don't feel comfortable putting in the comments, you can DM me and I will get back to you, or I can make a video of it walking you through that problem.